Today we're going to talk about graphing square root functions. A square root function is a function that contains a square root with the independent variable in the radicand. The most basic square root function is y equals the square root of x. And to the right of that you can see what that graph looks like. Since the value of the radicand in the square root function cannot be negative, the domain is the values that make the radicand greater than or equal to 0. So the domain must always be greater than or equal to 0. So the reason for that obviously is we can't take the square root of a negative number. So the radicand has to always be a positive number. So to find the domain of a square root function, we have to find the x that's going to make the entire radicand 0 or greater. So that leads into example number 1. So we're trying to find the domain of this function, which is y equals 3 times the square root of x minus 5. Well, the radicand is x minus 5. Right, that's what is underneath the radical sign. So because this has to be 0 or greater, we can just solve that expression for x minus 5 is greater than or equal to 0 to find out what is okay for us to have. So if I add 5 to both sides, that tells me that x has to be 5 or greater, so my domain of this function is x is greater than or equal to 5. Now compare that to what we first started out with when you looked at the y equals the square root of x up above in the graph. When I look at this function, the radicand is just x underneath. So in this case, our domain would have been x is greater than or equal to 0, because the radicand is just the x, and as long as it's 0 or greater, then we can say that that is fine. So next we want to talk about comparing graphs of square root functions. So first what we want to do is graph y equals the square root of x plus 3, describe the domain and range, and then compare it to what the y equals the square root of x parent function looks like. So again, just thinking about our table, if I just plug in my numbers, then I should be able to come up with the y values that go with it. So the square root of 0 plus 3 is going to be 0 plus 3, or 3. When I move on to 1, square root of 1 plus 3 is going to be 1 plus 3 is now 4. When I move on to the next one, and notice that I'm jumping to 4s for my x values. Reason for that is to make sure I'm thinking perfect squares, so I don't have to deal with crazy decimals. Square root of 4 is 2, plus 3 is going to be 5. The next one is going to be the square root of 9 plus 3 is the square root of 9 is 3 plus 3 is 6. And lastly, the square root of 16 plus 3 is going to be 4 plus 3 is the 7. So there's the table. And again, notice that we're using perfect squares in this case to try to help keep our numbers a little bit easier to manage. So notice here I've already done the two graphs for us. The one we're comparing to, which is the y equals the square root of x, and also the y equals the square root of x plus 3. The red one is the one we are working on. The original one, which is the one we're comparing to, is the black dashed lines. We don't have anything going on the x is negative side. Again, basically, if I was to plug in a -1 for my x, I would be stuck because I would have the square root of -1 plus 3, which I can't do with all our real numbers, so that's why we don't have anything on the negative side. But that would be our two graphs to start with. Then I want to focus on our domain. Okay, so our domain in this case is going to be x's are greater than or equal to the 0. And notice from our range, when I look at my graph, in this case our y's are greater than or equal to 3. So what we want to notice, which is things we've been seeing a lot with our quadratics, as well as our different types of functions throughout the year, as well as our absolute value functions, is that when I see a plus 3 on the outside, notice the graph is translated up 3 units. And again, that is simply because the plus 3 is on the outside of the radicand. Okay, so that's going to give us the vertical translation of an up 3 with the exact same y equals square root of x. The plus 3 jumps it up 3 units. For this next example, we'll notice that we have a little bit of a different look. We have a negative out in front of our square root, which is okay. And then we also have a negative 2, this time underneath the radical, which means we're going to have to think about it before we start doing anything with taking the square root. So again, I'm just going to kind of run through my points. If I think about my numbers that will help get me nice perfect squares, I'm going to put in 2. Because when I subtract 2, I get the negative square root of 0, which we know is 0. If I move on to the 3, and I'm using 3 because I'm thinking ahead to say that 3 minus 2 is going to give me another perfect square. The negative square root of 1 is negative 1. If I plug in a 6, I'm thinking ahead again to think that that's going to give me the negative square root of, the negative square root of 4. I'm writing it as I'm saying it, which is a negative 2. If I move on to the next one, then I'm jumping to the 11 again because I'm trying to get that perfect square. When I subtract, I get the negative square root of 9, which is a negative 3. And then the negative 18 minus the 2 gets me a negative square root of 16, which gives me negative 4. So then I can just plot these points and see what the graph looks like. So here you have your graph. I put those on there for you. The first one, obviously, the y equals the square root of x is in the dashed black dots. Again, showing us what we're comparing to. But the red is showing us something where we're kind of dropping down all of a sudden. When you think about this, we first would say, well, we can't have negatives, but that's really what we're talking about with things underneath the radical sign. So because that negative square root's out in front, we can have negative y values. We just can't have the negative x values inside. The other reason, when you think on this graph, when I look at the x equals 1, if I was to plug in x equals 1, my radicand is now 1 minus 2, which is a negative 1, which is why we don't include 1 or 0 in this case, whereas we did in the previous one. So here's a couple of things we want to look at on this one. When I talk about my domain and my range, the domain in this case, x's are going to be greater than or equal to 2. If I do the range, we're looking at y's are greater than or equal to the 0. So again, when I look at my domain, anything that is less than 2 is going to give us a negative in the radicand, which means we can't do it. Okay, but so some very typical things when we compare, we've seen this year. The going down, we're going to call it flipped down. Basically because we are doing the negative square root, right, which is like that negative a value in the front. We are translated, this time there's no vertical translated because we don't have anything on the outside of the radicand, but this time you'll notice that we are translated 2 units right, and that again is very similar to our quadratics and also to our absolute values, because when we have something on the inside, when we have the negative 2 under the radicand, we move, we don't more, we move two units right. So horizontal translation when it is underneath the radicand. So that's the square root functions. Again, a lot of the same characteristics we've been seeing throughout. So we just want to continue to notice those. One of the things you want to kind of keep working on is just making tables. Sometimes will make the easiest way to get your graph. Might not be the fastest, most efficient way, but it is certainly a way to start getting what the graph looks like on the paper, and then hopefully you'll start recognizing those characteristics. The negative in front would be flipping our problem down. A plus or minus on the outside is doing your vertical translation, and when you have the plus or minus underneath in the radicand, that is going to be your horizontal translation.